Welcome everyone to this session on weather, an appropriate topic for anybody based in Oxford, but really for anybody else these days. We're going to wait a couple of minutes for people to filter into this session. And in the meantime, while we're waiting to get started, let me just say a word about the format. We've got 4 really interesting papers, and I think a session that's where there's a lot of overlap on the topics that people are looking at. Each of the speakers is going to talk for 15 minutes, so making 60 minutes in total, and that should leave us pretty close to half an hour, even allowing for time for setup and closing. We should have a decent amount of time at the end for conversation. Please put any questions in the Q&A, so I will see them there. If there are questions that are kind of urgent clarifications, I'll try to pick them up and interrupt the speakers, but mostly I'll just let them carry on. And then at the end, I'll try to moderate the Q&A and make sure that any questions that are there in the Q&A get addressed to the extent possible. Please do be aware that the session is being recorded. So if we ask you to, if you end up putting your question to the panelists out loud, you will be forever recorded, and your question will be there in posterity. So with that said, thanks for joining us, and we'll wait another minute or so, and then I'll turn things over to Musa. So just a moment here. I'd also encourage those of you who are in the audience not to be shy about asking questions. Presenters are, love to know that there's somebody live out there paying attention, and we'd love to hear from all of you. So Musa, I'm going to go ahead and stop sharing those slides. Do you want to put your slides up? And we'll just, fantastic. I think we're at the 3-minute point, so I'm just going to say, take it away, Musa. It's all yours.
Thank you very much. So good morning or good afternoon, depending on your time zone. So the paper I'm going to present is entitled Current and Past Climate Variability and Malnutrition Among Farming Households in Ethiopia. And my co-authors are Stefan and Franziska. So first I will present an introduction that summarizes existing literature and the motivation. I will also discuss methodology in which I will present the data and the methods that I have used in the analysis, and then I will present the results. Finally, I will provide conclusions. So as an introduction, a recent publication from FAO shows there are more than 250 million undernourished people in Africa, and the figure is growing at a fast rate. And several studies also showed that weather variability is the major cause for the malnutrition in the continent. The same is true for eastern part of Africa, and this specific region, drought is becoming more frequent and severe. And numerous studies have also examined the effects of weather variability on food security, nutrition, especially by focusing on anthropometric indicators and diet quality. However, most of those studies examine the effects of weather variability by focusing on a single year shock, by disregarding the influence of past weather variability. But since most of agricultural decisions are made based on farmers' expectation about the upcoming weather condition, past weather might also affect the availability of food. And again, recurring past weather shock could also leave households with inadequate time to recover. Hence, it is important to separate current and past weather, the effects of current and past weather variability on farm households. And we have few existing studies that emphasized on the effects on agricultural productivity, rural livelihoods, such as income from off-farm and non-farm activities, and effects on farm income and rural poverty. But weather variability could also affect consumption, since production and consumption decision in smallholder agriculture settings are not separable. Hence, in this study, we will focus on the effects on the availability of macro and micro nutrients. The reason why we are focusing on nutrition is nutrition by itself is a valuable development indicator. It's also a vital contributor to development. We have several studies that shows undernutrition, especially in childhood, would cause irreversible adverse effect in birth weight, lower educational achievement, cognitive skill, productivity, and earnings. So from policy perspective, this will be our contribution. And the reason why we are focusing on Ethiopia is, again, weather variability is very common in the country, and rainfed agriculture is the main source of income for most of households living in the rural areas of the country. Again, there is unacceptably very high risk of malnutrition and deficiency of essential micro and macronutrients. And recent publications also shows the country is off track to achieve most of the nutritional targets of the Sustainable Development Goals. The other reason is, again, we have detailed panel data collected in those years. So our main data comes from LSMS World Bank survey, which is collected by Central Statistics Agency of Ethiopia, which provide a very rich georeferenced data collected at household, plot, and community levels, which covers almost the entire parts of the country, except those which are communities who have non-sedentary way of life. Apart from that, the survey covers the entire parts of the country, which gives an interesting spatial difference in terms of agroecology and other aspects. In terms of weather variable, we rely on SPI, which is standardized precipitation evapotranspiration index. The reason why we choose this index is recent evidence from both developed and developing countries shows rainfall is not the only factor that determines agricultural productivity. So we have to account for the other elements, especially studies conducted in Eastern Africa shows agricultural productivity in the region can only be explained by a complex link between precipitation and temperature. So we use this index, which provide a more reliable indicator by estimating deviation from total precipitation and evapotranspiration from their historical mean. As a result, we consider growing season weather condition as a current weather variability indicator, and the preceding 10 years will be considered as past weather pattern. Again, we rely on existing literature to construct our current and past weather variability. And this is the index for the current weather variability. As you can see from the figures, there is noticeable weather variability in those three surveys, especially in 2013, there was a positive, green and blue shows positive water balance and red shows negative water balance. So there was visible variability in terms of current weather variability. In terms of nutritional indicators, we relied on, again, previous studies and deficiencies of essential nutrients in the country. For instance, the national, in the country, the zinc deficiency is considered as a national problem. So we relied on those reports and existing studies, and we identified the availability of calorie, protein, iron, zinc, and calcium as our indicators of the nutritional status. For the analysis, we relied on household fixed effects, which enable us at least to account for any time invariant household heterogeneities that might affect consumption pattern and the extent of the effects of weather variability. It also helps us to account for factors that can influence the types of food available in the community. So this is the first results, which shows the effects of current weather variability on nutritional status, and we couldn't find a significant effects of current weather condition on the availability of macro and macro nutrients. And we estimate the same equation by changing the definition of the weather variability, like by creating binary indicator, or we also use subjective indicator, and we created categorical indicator. But in all cases, our results shows farmers smooth nutrient availability from adverse current weather variability, which is again consistent with a recent study from Cambodia, which shows household protein consumption from current weather variability. And we also looked into their coping strategies, and we found that less than 1% of households changed their consumption pattern to cope with drought shock. But we found that strategies which could affect their capital productive assets, like selling agricultural assets, livestock, or using credits and saving, were found to be the major coping strategies. So if there is repeated adverse weather condition, this might lead to a deterioration of nutritional situation. And we found again, yeah, this is the effects of past weather variability in the availability of nutrients. So we found statistically significant effects of past weather variability. Apart from that, we also looked if there is, if adverse weather variability stimulates the response that might associate with deterioration of nutritional status. In particular, we examined if there is a link between their land allocation decision and market participation rates. We found that both the size of land allocated to the production of non-stable crops and their market participation rates found to be adversely affected by past weather condition. So we found that households' nutritional status is more sensitive to past weather variability than current weather condition. And our results also shows that past weather variability reduce their market participation rates and increase dependency on low value, less nutritious, stable crops, which means the results indicate that climate variability is imposing challenge to the country to achieve some of the development goals, like sustainable development goal. So the policy implication is that also, although farmers can withstand the effects of current weather variability, either through relying on their own coping strategies or by relying from the support from government and government organization, in the long run, weather variability could aggravate the problem of malnutrition. As a result, policies that focus on agriculture development or promoting nutritional status in rural settings has to recognize both the current and past weather variability. Yeah, thank you.
Thank you very much, Musa, and thank you for sticking not only to time, but actually you're a bit ahead of your time. Given that, before I move on to Jules, there is a question from Jeff that is about the source for the SPEI data, the SPEI data. Can you just say a word or two about where those data come from?
Yeah, they're publicly available.
Okay, but it's not. And if you want to dig around for it, maybe I'll just let the two of you connect bilaterally. But
yeah, let me stop sharing.
Good, wonderful. So let's just move on. We'll come back with Q&A for the whole group at the end. And Jules, let me go ahead and invite you to share screen and to unmute and turn your video on so we can watch you presenting.
Yes. Yes. So about the video, it seems I have a problem because I tried to connect, but it says that I cannot.
We will just imagine you in visually, and go right ahead. You've got 15 minutes.
Yes, so, sorry about that. So thank you, Doug. I'm very happy to present this paper today in this session. So it's joint work with Pauline Castin, who was a colleague at CERDI, and is now moving to the World Bank. And so my name is Jules. I'm a postdoctoral fellow at J. Palmina. So the paper is Index Insurance and Agricultural Decisions, assessing the external validity of multiple randomized control trials. And so we know that in low and middle-income countries, access to formal insurance is extremely limited. And farm incomes, as a consequence, are particularly vulnerable to weather shocks. Farmers, they often resort to a self-insurance mechanism against risk, and this is often done at the expense of productivity gains. For instance, they adopt technologies that have low risk but low returns. Against this background, index insurance have recently been an innovation that have been drafted. So unlike traditional insurance that pays off individual farmers on the basis of their loss, index insurance, the idea is that it will compensate people based on an index that is designed to be highly correlated with the losses of farmers, but not identical. And this has been shown to have three main advantages. The first one is to reduce transaction costs. The second one, to reduce information of asymmetries. And the last one, adverse selection. And these products have very rapidly spread in recent years. There is growing evidence in the literature that index insurance can help farmers to cope with weather shocks and also to foster the adoption of more productive techniques. However, something important is that each study is rooted in a particular context, in particular, the period, the location, and the interventions are specific. And so one question is to what extent the estimates that are present in the literature are informative about impacts in other settings. So what we do in this paper is that we use data from 6 randomized control trials on index insurance to explore 3 questions. The first question is, what is the average impact of index insurance on production decisions? The second, what is the true heterogeneity treatment effects across studies? So that's how we define external validity. And the last is, what are the sources of heterogeneity in treatment effects? We use a Bayesian hierarchical model to disentangle the true heterogeneity in treatment effects from the pure random sampling variation that are due to the use of sampling techniques, for instance. We find 3 main results. The first one is that the average effect of index insurance is positive, although more uncertain than previously believed. External validity is limited. Actually, we found that the bulk of the variation in treatment effects is actually true heterogeneity, and only 42% of the variation in treatment effects is sampling variation. Finally, we explore the heterogeneity treatment effects, and we find that treatment effects tend to be larger for households that are worse off, and also for households with a low predicted levels of outcomes. And of course, I will give more details on that. But there are 3 main contributions of our work. The first is to add to the literature on index insurance. And so we assess the average effect of index insurance on production decisions more systematically and look at the external validity of the results. Second, we provide another example of how Bayesian models can be used to aggregate information from multiple experiments to explore the extent of external validity. And finally, we show how pre-registration can be used to conduct meta-analysis when the original data that have been collected are actually not publicly available. So how did we select the study? So we consider as eligible the studies that meet 3 criteria. So studies that increase farmers' access to index insurance, studies that are designed as randomized control trials, and studies that measure impacts on farmers' production decisions. And so after our selection process, we identified 10 eligible studies. So 4 eligible studies in the review conducted by JPAL, and then 6 eligible studies that were citing the studies in JPAL review. And to back check that we were not omitting studies, we actually also conducted independent literature searches on Google Scholar and find no excluded eligible studies. So we pre-registered the study in June 2020, and then we made formal data requests to the authors of the studies. And for 6 of them, the authors actually accepted to share their data with us. So about these 6 studies, so they cover very heterogeneous context, so 6 countries actually. Their design is also quite different. So 4 studies are designed as price experiments, while 2 provide access to free insurance. And actually, there are also 2 studies that cross-randomize additional treatments. The eligible criteria also vary largely, and the sample. So, but in general, the common framework are smallholder farmers in low and middle income countries. The sample size also, there was some variation there. And so overall, the question we ask is trying to understand how effects differ across the studies, how important is the heterogeneity, and what is the average effect of index insurance. So our framework, the basic framework is pretty simple. So we are interested in the effect of randomly assigned increase in access to index insurance on agricultural decisions. So I will give more detail on what is the outcome variables and what are the outcome variables later. But for now, we are interested in this coefficient tau k, which corresponds to the ITT effect of offering index insurance to household I in study K. And so we define true heterogeneity in treatment effects, so the quantity of interest, as sigma tau square, so the variance of this tau parameter across studies. And this quantity, we argue, provides a natural measure to gauge the level of external validity of the evidence. The problem, however, is that this individual tau 1, tau 2, and tau k, so we have 6, 7 tau, they are unknown. And what we can observe is only estimates of these parameters because, of course, there is sampling variation. And so in practice, what this will lead is to overestimate total heterogeneity. And so it will overestimate sigma squared tau. The nice thing about the Bayesian hierarchical model is that it offers a statistical tool to actually disentangle the true heterogeneity in treatment effects from the sampling variation. And so in contrast with more classical meta-analysis, so fixed effect or pooling models, which consider that individual studies estimate a common effect, in the hierarchical model, we allow for the presence of heterogeneous effects across studies. And so the typical setup can be summarized in these 2 lines, which basically means that each individual study estimates its own treatment effect, tau k, and then in turn, each individual treatment effect is drawn from a common distribution. And so this is why it's called the hierarchical model. There are these 2 levels, this hierarchy of effect and assumptions. And so what we can observe is tau k at and the sampling error at by study. And then the other parameters, they need to be estimated. And just one note is that this model, one of the nice features of this model is that it can recover the results of classical meta-analysis. Namely, if there is no heterogeneity in treatment effects, it will find that sigma squared tau is equal to 0. And if there is a lot of heterogeneity treatment effects, it will recover the results of the initial studies. So to estimate the model, we follow Michler in particular and incorporate more structure to the model by using the original data from each study. And so we analyze what this allows us to do, to have the data, is to analyze outcomes that were not included in the original studies by the authors, also to standardize the outcomes, and finally to incorporate household level covariates to explore the source of heterogeneity in treatment effects. We use the Bayesian estimation method, and more practically, we use the Bagger R package that Michler and Visek recently developed. About the outcomes, so we consider 5 outcomes that are available in all studies, and so this is something that we actually go into details more in the pre-analysis plan in our pre-registration. But so the 4 main first outcomes, they are pretty straightforward. So it's the area cultivated, the amount of fertilizers, the amount of pesticides that are used, and the amount of seeds. And then we also added this 5th outcome variable, the crop portfolio riskiness. And so here the idea is to capture the level of risk that farmers decide to take on when they are covered by insurance in their crop decisions. And so there are crops that are more risky than others, and to have a proxy of the risk of each crop, we look at the coefficient of variation of the yield of this crop. And so then we do a weighted average of the different crops in the portfolio, weighting by the amount of land devoted to each crop. So there are 4 main sets of results. So first I will present results on the average treatment effect of index insurance. And so here I summarize the results for the 5 outcomes with the effect size. And so there are 2 main estimates for each outcome. So in green, it's the result of a classical meta-analysis, so the pooled OLS, and in blue, it's the results from the Bayesian hierarchical models that relax the assumption of no heterogeneity in treatment effects across studies. And so what we can see is that overall, there is a positive effect of index insurance. So this is consistent with the literature so far. But when we relax the assumption that studies estimate the common treatment effect and that there is no heterogeneity, we see that there is a more uncertainty in the effect. As you can see, the confidence intervals are larger in the Bayesian hierarchical. So then we report more systematic statistics on the heterogeneity in treatment effects. So here we use estimates of sigma squared tau from the model to gauge the extent of external validity. But one question is what constitutes a large or small value of sigma squared tau? And so to interpret the magnitude of this coefficient, we define the pooling factor as the sampling error, the estimate of the sampling error divided by the total variation in treatment effects. And so the nice thing is that it gives a value between 0 and 1, and actually a percentage of the total variance that is explained by sampling variation. And so what the main result here is that average across all our outcomes, so our 5 outcomes, we find that 42% of the variation in treatment effects is due to sampling variation. So there are some variation between outcomes, as you can see in the coefficients I report.
About 3 minutes left.
Okay, great. So it seems that overall, a majority of the variation in treatment effects is due to true heterogeneity in treatment effects. Next, we look at the sources of heterogeneity in treatment effects, and in particular, we look at we look at 5 variables that would explain this heterogeneity: wealth index, household size, the age of the household head, literacy of the household head, and predicted outcomes. So predicted outcome is a simple regression of the outcome at end line for the control group, predicted using a bunch of predictors. And then we do that also for the treatment group and divide in 2 groups with respect to their mean. So groups with high value of predicted outcomes or low values. What we find is that the treatment effects, they tend to be larger for households that are worse off and for households that have low levels of predicted outcomes. For the other variable, household size, age, and literacy, we see no big sources of heterogeneity here. So these are the results graphically. They are in the paper, so if you want to have a closer look. And finally, so the last result on the predicted effect of index insurance in a new study. So here we want to know if we were to conduct a new study in a totally different setting, what could we predict in terms of expected effect based on the evidence that is already available and based on the heterogeneity that was estimated across these studies. And so again, here I report the pooled OLS just to put the estimate in perspective. And what we see is that here there is a massive uncertainty actually. The confidence interval in the Bayesian hierarchical model are very large. Just to take an example, so for the last one, cultivated area, we see that the mass probability of an effect between 0 and 0.2 is 50%. But then there is also 25% of probability that the effect size is negative and 25% that it's above 0.2. So it's what it means that it's very important also for this new context to try to have some evidence on the effect, because we cannot only rely on the evidence that is already available. So quickly, the key results. The effects of index insurance on production decisions are generally positive. However, as we saw, there are more uncertain once we allow for the presence of heterogeneous effects across studies. External validity is rather limited, and treatment effects, they tend to be larger for worse off households and for households with low levels of predicted outcomes. And finally, the predicted effect of index insurance in a new study is quite uncertain. And so it's important to get evidence from additional settings. There are two limitations. So first, there is not enough studies to explore whether and how study level coverage drive heterogeneity in treatment effects. What we think is that, of course, it's a big reason for why we see heterogeneous treatment effect is difference across studies, but with 6 studies, we are very limited in our ability to explore this quantitatively. And then is that the results are specific to our cities. There are some new methods that are being created to aggregate data also using observational and quasi-experimental studies. But in this study, we were not able to incorporate them. Sorry. Thank you very much.
Thank you very much, Jules. Really interesting, and I think both substantive connections to the other papers, but also a really nice methodological contribution here that opens the door to asking a bunch of questions. So without further ado, though, let me move on and ask Wataru to share your slides, and we'll let you pick it up for the next 15 minutes or so. And for audience members, please feel free to put stuff in the Q&A. We'll look forward to kind of a robust discussion at the end. But all yours, Wataru.
Thank you. So good morning or good afternoon, everyone. My name is Wataru Kodama. I'm a PhD candidate. And today, I am very happy to present my study titled Basis Risk and Low Demand for Weather Index Insurance. So let me start. So for the background of our studies, we consider rain-fed farmers in rural Africa who are facing severe climate risk. And in such a context, weather index insurance has been seen as one of the promising policy tools because of its insurance design. In the rainfall index insurance payouts are based only on officially observed index. And so there is less concern on moral hazard problem and then less monitoring costs. So insurance company may provide insurance with affordable premium. So that's a basic story of the weather index insurance. But in the literature so far, we see a pretty low demand in spite of a large potential benefit. Maybe this statement is not really good after the presentation pretty good presentation by Jules. But the point is that we observed a pretty low demand on the weather index insurance. And of course, there are very a variety of the discussions, but basis risk is one of the main concerns to scale up the insurance demand. So what is basis risk? So basis risk is, as I define here, it is a risk of no or under insurance payout when farmers incur loss. So in order to understand the idea, I show a figure. So consider rainfall index insurance. In the rainfall index insurance, insurance payout are determined, for example, based on the rainfall at the weather station. But what matters for farmer is, of course, the crop yield at the plot level. And then this crop yield is largely determined by the rainfall at the farmer's plot. So it is pretty likely that the correlation between the rainfall at the weather station and then actual crop yield at the plot level is not well correlated. So that's the source of the basis risk. But so far, I'd say that there is only limited evidence to show the impact of the basis risk on the insurance demand. So our research question is very simple, which is how much does the basis risk affect demand for weather index insurance? In order to answer this question, we focus on maize farmers in rural Zambia, and then we saw the rainfall index insurance for 3 years. So here's are some of the contributions, but our most important contribution is that we were trying to precisely estimate the impact of the basis risk, and then we also consider how much it would be, how we can improve the welfare of farmers by reducing the basis risk. Okay, so I start with my theoretical model. So for a model, I consider risk-averse farmers who want to maximize their expected utility, and in order to choose their optimal insurance demand, which is alpha. So their utility level is defined over Y and L. So Y is a crop harvest in normal year, and then L is a crop loss in drought year. So we only consider this binary case, a normal year and drought year. And then, so in drought year, they have Y minus L crop harvest. And they are going to choose the optimal insurance units. And then this alpha could also seen as insurance demand. And then also P, Q, and R are probability, pretty important probability factors. So what are P, Q, and R? So before talking about these probability factors, I introduced the Clark's four-state model in order to model the insurance that accompany the basis risk. So in this model, we only consider the only 4 states of the world. So we only consider whether farmer experience loss or farmer experience drought or not, and maybe insurance provider gives a payout or not. So 2 times 2, we have 4 states. And of course, for the farmers, the worst case is the first case where they get lost due to the drought, but at the same time, they don't get the payout. And then this case is known as a false negative. So now let me introduce P, Q, and R. So first, P is the probability of drought. Q is the probability of payout. And in our context, we saw the same index insurance to all the farmers. So Q is fixed across farmers. And last, the most important one, R, is the probability of false negative. So this is the joint probability that farmers experience drought, but they don't get payout. And then this R represent the basis risk in our paper. So what is good about this introducing this P, Q, and R is that we can define the probability for corresponding to the each 4 states of the world. So with the payoff for the different states of the world, and then the payoff corresponding to that state, we can merely sum up these payoff and then define the expected utility. So now farmers are going to maximize their expected utility and choose their alpha. So this is a demand function. Actually, we don't have a general solution, but if we focus on the fair index insurance, we have this closed form solution. And we have interior and corner solution. And then the corner solution basically means that they don't purchase any insurance product. So looking at the interior solution here, the first implication is that the basis risk, or the R, which is a probability of false negative, decrease the insurance demand. And what is more important is that the effect is proportionate to loss, which is L here. And then we also have like other implications, like conditions for uptake. But our main focus on the Implica framework is to test the first implication. Okay, so now let's move on to the Implica framework. So now we have this demand function. And then our main focus is, of course, R, which is a basis risk. So for data, we use household data, including the actual sales of rainfall index insurance for 3 years. And then we actually saw the index insurance, the same insurance product for all the farmers. So it's not really like a RCT, but the important thing is that we changed the insurance design across 3 years. So how we change it? So this one is a map of the study sites. Our households are staying in village 1 to 5. They are relatively close, but they have a different elevation level. So that is actually a source of the different rainfall pattern. And for the first 2 years, referred weather station was Choma, which is relatively far from most of the villages. But in last year, we changed the referred weather station to Marima. So the payout is determined by the rainfall at Marima in last year. And we also changed the threshold for the payout, but that's a trivial one. So the basic idea is like, for example, like for farmers who are staying in village 1, they have like a relatively higher basis risk for first 2 years, but in last year, they have like a less basis risk because of the change in the weather station. I mean, referred weather station. Okay, so the point is that we have this within household variation in basis risk over the years. And we, using this within household variation, we can test how households respond to the change in the basis risk. So based on this idea, this is the baseline specification. So this is the simple fixed effects model. And following the demand function, I include the interaction term between the R, basis risk, and then the loss here. And then this error term is correlated within household, within the same household. So if the farmers are really responding to the change in the basis risk, we expect that this beta 1 to be negative. Okay. But when we look at the demand function, we also realize that maybe the P, which is the probability of drought, also plays an important role. But unfortunately, we don't have within household variation for P, because maybe we can expect that the farmers has the same probability of drought across 3 years. So we cannot really run the fixed effects model. So we merely have this pool OS to test a model prediction in this way. And if we find like these correlations, then we can say that maybe the data is kind of supportive to our demand function. So, but looking at like this, our specification, you can imagine like we have data on alpha. And then also maybe we can ask farmer, what is L? But we don't have data for P and R for our empirical estimation. So what we need to do next is we need to estimate or quantify P and R for specific farmer. So again, P is a probability of payout, and then R is a probability of false negative. And in order to estimate P and R, I combined two rainfall data sets. The first one is the historical rainfall data at weather station, and another one is the plot level rainfall data, which was collected prior to the index insurance sales. So how we did this? Actually, we installed this plot level rainfall gauge, and then we observed the rainfall pattern for a specific plot. And then the good thing about it is that we can also see how it relates to the rainfall pattern at the weather station level. Okay, so what we need to do next is like just assume import some assumptions. Maybe I should explain only for P. So now for the probability of drought, we assume like the farmers experience drought when their rainfall, plot level rainfall RI is less than the certain amount in a specific time period. And then this RI follows a specific probability distribution function. So with these assumptions, we can estimate the probability of drought in equation 4. And then same logic can be applied for the probability of false negative. So what we need to do is like, again, we need to assume like, I mean, this is like based on the insurance design, but we can say like insurance payout is based on the rainfall at the weather station level, and then the threshold is like this. And we need to assume the specific joint probability distribution for the rainfall at the plot level and the weather station level. So this is how we can estimate the probability of false negative. Okay, so data, I should make it very briefly, explain it briefly. So we use 5 villages in 3 sites in Southern Province. And then why Southern Province? Because it is the most drought-prone area in Zambia. And then we focus on the rainfall-based farmers. For the insurance sales, we sold fair insurance for 3 years. And then the premium was set pretty low so that everyone would purchase the insurance at least like 1 unit. And it was like $1 per unit. And then the payout per unit was like $3 to $5. So we expect farmers to purchase a lot of insurance. But descriptive statistics, on average, farmers purchase only like 2 to 3 units. And then we also ask farmers, how much do you expect to lose in drought year? Then they answer like they expect to lose about 1.1 ton. And then this is equivalent to like 68% of normal harvest, harvest in normal year, which is also about the $170 on average. So this means that because we only like the payout per unit is only like $3 to $5, basically it means that this insurance product covers only like a 4 to 8% of the expected loss. So consistent with the literature, we see a pretty low demand.
Just about 3 minutes left, which looks like it should work fine.
Thank you. So for the base, so now let's see the result. So for the baseline specification, so this one, we see a significant impact of the basis risk. And then this is relatively consistent across the different specification. We also control the risk averse, the degree of risk aversion, and then also the cash transfer. So here, but if we look at the coefficient, if we interpret the coefficient, we can realize that the economic impact of reducing the basis risk is pretty limited. So like consider like 5 percentage point reduction in basis risk. This is like halving the basis risk in our context. This result lead to like a 31 to 38% increase in units. So maybe this is not bad, but if we look at the coverage, like how much it covers their expected loss, we only like expect like only around 2 percentage point increase in coverage. So maybe like having the basis risk is a hard work, but it only brings about like this percentage point limited economic welfare. For the testing model prediction, we find a significant and supportive correlations. Okay, so conclusions. So we have 2 main main findings. The first one is that yes, basis risk has a significant and negative impact on the insurance demand, consistent with our model. But reducing the basis risk has modest welfare impact. So for simplification, maybe minimizing the basis risk is not really our perfect ideas, considering the associated cost for doing so. So future work, we need to identify cost-effective interventions rather than merely reducing the basis risk. And of course, our study is based on a sample from a specific site in Zambia, so external validity should be confirmed in the future study. That's all. Thank you so much.
Thank you very much, Wataru. Really nice, really interesting, and again, I think some great overlaps across the papers. I would again encourage people in the audience to put questions in the Q&A. Otherwise, we'll also be open to having panel members putting questions to each other. So I think there'll be a conversation to be had. In the meantime, Jeff, why don't you go ahead and share slides and take it away.
All right, thank you. I'm glad that we can all be here together virtually, if not in person. Hopefully next year we can all be in Oxford together.
Looking forward to it.
So I'm presenting today work with Anna Josephson, who's here at the University of Arizona, Talib Kilic and Siobhan Murray, both at the World Bank. This is one piece of a much larger project which we've been working on for many, many years, trying to understand ways, measurement error that occurs when we're integrating remote sensing weather data with the survey data and using the LSMS as a reference point. So what I'm going to be specifically talking about today is the role that privacy protection measures have in creating measurement error and creating uncertainty in the results or our use of remote sensing data in economic contexts. So economists love to use public use data sets. They're a great resource for economists. They're used with the internet and computing power. They're more and more available, and they're used more and more. The US, a lot of researchers use the US Census data or the annual business survey. As development economists, we're often relying on the DHS, the World Bank's LSMS, which is Musa's data was from. But these public use data sets, before the data can be released, administrators need to ensure the privacy of the participants in the survey. For the US Census, the need to protect privacy is codified in law. For the World Bank, USAID's DHS, these things are determined by ethical review boards. The way people or administrators protect privacy for participants in the survey is by injecting or introducing noise into the data. And so typically the effect of privacy, the ways to protect privacy and the effects of privacy protection on data has been the realm of cryptographers and computer scientists. But in 2018, the US Census Bureau announced that they're moving to what's called differential privacy. And that privacy protection system has created a lot of concern and reflection in US economists to figure out, well, how is this going to affect our use of the data if this sort of noise gets introduced into the data? That's suddenly woken a bunch of us up to be like, hey, well, how is privacy protection happening in the DHS and the LSMS? And so they don't use what's called differential privacy. They use other privacy protection methods like SDL, statistical disclosure limitation. And for people, those of us who want to connect remote sensing data with the public use data sets, DHS and LSMS use what's called K-spatial anonymity, which means they introduce noise to the actual locations of the household so that you can't re-identify the households. The thing is that the more accurate the data, the more privacy is lost. It's a fundamental tenet of cryptography. The corollary of that is the less accurate the data, the more privacy is protected. And so there is a social welfare function that data administrators have to solve, which is what's the trade-off between greater privacy protection but less accurate data, more accurate data but less privacy protection. So this is economists are only now beginning to kind of get into this problem and think about these effects. And so we're looking at what's the effect of privacy protection in the LSMS when we try and match LSMS data to remote sensing data sources. How much noise does K-spatial anonymity introduce, and are maybe the results that we get simply due to distortions in the data due to these privacy protection measures. So you kind of visualize this. On the left side of the screen, I have just time slices from 6 different rainfall remote sensing sources. I'll frequently call them satellite sources, even though they're not all satellites, and 3 different temperature sources. And so you can see that the spatial resolution in these sources vary quite dramatically. Also note that the readings themselves vary quite dramatically. You know, this satellite reports 6 to 11 millimeters of rain, but this satellite reports, what, 39 to 46 millimeters of rain. It's the same day, it's the same location, but there's quite a bit difference in what different satellite sources are reporting as the actual rainfall in an actual location on a given day. So we'll come back to that later, but just now note the different spatial variations that we get. On the right side, I have a graph of a number of different ways the World Bank has used or is considering using to anonymize the location of households in the LSMS. So you can't really see the red little quote here, but that's the true household location of a specific household in the LSMS. And then the other hashes or regions are different ways that the World Bank has considered or does currently use to anonymize the household location. And you can see that depending on the anonymization method, you may end up with moving the household from one grid cell to another grid cell, or in this administrative area, the result would be an average of all the grid cells. And so you can see that there is the possibility or the potential for mismeasurement, or we're basically assigning the wrong rainfall value to a household simply due to the spatial anonymization method. And so what we want to do is like, it's possible, but does this actually matter in an econometric context? So our goal here is to provide guidance to researchers who are looking to integrate geospatial data with socioeconomic survey data and try and figure out, well, how big of a problem is this in the current data sets that we're using? And so the way we do this is we combine a number of different geospatial weather data sets from remote sensing sources with the World Bank's LSMS ISA data set. And our empirical context is we're going to regress yields, farm yields on different metrics for weather from different satellite sources. And so we're going to see what's the correlation between weather measured from different satellite sources, weather measured via different anonymization methods, and its effect on yields. And does its effect on yields change as we change the relationship between the matching and the data source? Good news is we do not find any differences based on anonymization method. Currently, publicly available remote sensing weather data sets are too coarse for the anonymization method to matter. You just don't, you can buy private weather data sets, and there the resolution is enough that it does matter, but in general economic use, public use remote sensing data sets, there's too coarse. So right now, anonymization methods do not matter. What we do find is that our results differ dramatically based on the source of the remote sensing weather data. So which satellite source you choose can dramatically affect your estimates. That should be a concern. So the way we did this, because it's the space of potential sources, anonymization methods, ways to measure weather, specifications are that possibility set is almost infinite. We filed a pre-analysis plan on OSF. So like Jules, it's not an RCT, but we don't have access to the true household coordinates. And so we think it's credible that those of us in the data analysis team, which includes Anna and myself, have no way to access the private information that the World Bank holds about the true locations of these households. We think our pre-analysis plan is credible, that we haven't done all the analysis first and then filed the pre-analysis plan second. And so we define in the pre-analysis plan the countries we'll look at, the remote sensing products we'll use, the anonymization methods we'll test, a whole bunch of different rainfall metrics, whether we're looking at the value of farm production versus the quantity, and a number of different specifications. This results in 51,840 regressions that we run. Again, this is a subset of a much larger project where we're running about 250,000. So we're going to focus on just two specifications, a linear with and without household fixed effects. And then because obviously, the returns to weather are probably, diminishing, we also have a quadratic specification where we look at weather and weather squared, again, with and without household fixed effects. So I'll just show you a very small subset of obviously 51,000 results. So with 51,000 results, we can't really look at normal, we can't look at p-values, I can't show you tables. So we had to come up with different ways to compare across regressions and across different regression results. So one way we thought of was, well, let's take the let's take the log likelihood in every regression, and let's take the average across a whole bunch of regressions. And the idea here in the specification chart is we've looked at all the regressions with using different anonymization methods. So here's EA simple, household simple, household bilinear. And so for each of these, we have 1,000 regressions, I forget how many exactly. Take the average log likelihood and see, does using one anonymization method versus another result in differences in the mean log likelihood of regressions? And as you look here, anonymization method doesn't matter, doesn't change the mean log likelihood of all these underlying regressions. This is for just weather by itself. If we look at the weather plus weather squared regressions, we again see, we're not explaining more or less of the variance in yields if we're matching the household data with different, with remote sensing data using different anonymization methods. Another way we can look at it is, does matching with different anonymization methods change the significance of the coefficient on weather? And again, we see, doesn't really matter across different anonymization methods, regardless of how we're measuring weather, regardless of what country we're in. Whether about 60% of weather metrics are significant, about 40% are not significant at the 90% level. At the 99% level, more than half of weather metrics are not significant. Only slightly less than half of weather metrics are actually significant at the 99% level. This is for rainfall. Here's temperature. Temperature plays a slightly larger role in yields. Trying to break down the data even more, I can actually show you coefficients on the weather metric for specific weather metrics. So here we're looking at just mean daily rainfall from regressions that include household fixed effects. And so in the specification chart, this top section is all the different anonymization methods. This section down here is the weather product, what remote sensing source it comes from. And then the bottom is whether we're using the value of farm production or the yield for the primary crop. And if you notice in Ethiopia, mean daily rainfall in general does not have a significant is not significantly correlated with yields or with farm value. And there's just kind of a cloud of noise for the anonymization methods, which says there's no sort of pattern. We don't get results. We don't one set of results for one anonymization method and a different set of results for a different anonymization method. But what you do see is strong patterns in the remote sensing sources. If you use the European Center for Mid-Range Forecasting's ERA 5 data, you get positive correlation between mean daily rainfall and yield. If you use CPC or MIRA 2, you get negative correlation between mean daily rainfall and yield. So if you're choosing you want to use remote sensing weather data as an instrument, you want to use it as control variable, depending on what source of where you take that weather data from, you could get rainfall helps crops grow, or you can get rainfall kills crops. Or for most places, you would get rainfall has no correlation with crops. We can see this, it's not an artifact of Ethiopia. We see this in Malawi. Now in Malawi, TAMSAT is the thing that kills crops. Rainfall measured by TAMSAT kills crops. Rainfall measured by AR5 increases crop production. So does CPC, though in Ethiopia, CPC rainfall killed crops. We can look at Niger. Here we have ARC2 making crops grow, TAMSAT killing things. A lot of stuff doesn't matter. Nigeria, Tanzania, almost no rainfall variable matters for whatever reason. You know, rainfall doesn't help crops, either helps or hurts crops in Tanzania. Uganda, we can look at growing degree days too. And again, the same sort of pattern emerges. There is no pattern among the anonymization methods, but there is strong patterns among the weather products. Growing degree days measured by CPC increases crop production in Ethiopia. The other ones don't really have an effect. Malawi.
Just about 3 minutes, Jeff.
Perfect. Here in Niger, growing degree days is measured by MIRA2, reduces yields or reduces crop production. Growing degree days measured by CPC increases crop production. Again, not an artifact of a single country or a single way that we're measuring, whether we're measuring value or yield. It's also not an artifact of whether we have weather and weather squared, whether we have fixed or not fixed effects. I'm just showing you a subset of the data, but these are indicative of all the rest of the data, which is in the paper. But these are consistent trends that we see that span countries, that span time, that span whether our specifications, that span our measurement of the output, and that also frequently span different weather metrics. I didn't show you this, but we tried 22 different ways to measure weather. Mean, variance, dry spells, z-scores from long run deviations, a whole bunch of different ones that you can look at the paper. And these sort of patterns continue to emerge regardless of our specifications, our choice of weather metric, things like that. So the takeaway from all this is that currently, with the resolution of remote sensing weather data, we do not need to be concerned about these anonymization methods. You know, right now, as we move forward and remote sensing weather data sets become more and more high resolution, right? We're in remote sensing weather data resolutions, you know, a half a degree. If we were doing land use, Landsat is 30-meter resolution, right? That's very high resolution. So right now, weather data sets are not very high resolution relative to other satellite sources. So now we don't need to care about it, but in the future we may need to worry about the noise introduced by these anonymization methods. What we do need to worry about now is that our analysis may be an artifact of what remote sensing source we choose. If I choose chirps, I might get, you know, a positive correlation. If I choose TAMSAT or ARC2, I might get a negative correlation between my weather measure and my output. And I guess when we're thinking about choosing instruments and using weather as instruments, we could basically get whatever result we want by simply cherry picking the remote sensing data source that gives us the correlation, the first stage results that we want to get. And so we should be careful, and we may need to demonstrate our results are robust to different choices in remote sensing product, right? In the same way we do robustness checks for a whole bunch of other things, this means we may need to say, well, it's not just, my results are not an artifact of me choosing one remote sensing source. I could choose another one, I get the same result. So I'll stop there. I know there's a lot of information very quickly, but thanks for your attention.
Thanks very much, Jeff. Really, really interesting, really thought-provoking, really disturbing in some important ways. Can I just, I'd like to throw this open for discussion with the massive crowd that we have left. And we've got about 20 minutes for conversation, but can I just abuse chair's prerogative and ask a follow-up question for you, Jeff? I couldn't understand whether what you're referring to, maybe you can't actually distinguish this, whether this is about the ultimate observed weather from these different sources, or about the modeling that's being used to map observed weather into grid cell specific. And right, there's some combination. Most of these are products that take some observations, match them to models, and interpolate and extrapolate back in time. And so is the question, they have different observed inputs, or is it the modeling and smearing that's going on?
So ARC2 and CHIRPS, and I believe TAMSAT have all very similar inputs. And there's slightly differences in modeling, but the actual optical or infrared inputs I think are the same across those three. And we see those three tend to agree with each other. Where we see big differences are in the reanalysis data sets, which are ERA5 from European Center and MIRA2. So those are reanalysis data sets. I have historically used either CHIRPS if I just want rainfall, or ERA5 because ERA5 has SPEI, it has Palmer drought indices, it has wind, it has a whole slew of useful variables. But what we're finding is that reanalysis really results in dramatically different estimates when you're looking at a very specific point in space. And so maybe for landscape areas, those things are really good. But when you're looking for, I want to know what happened to this household at this time, we get dramatically different results. I get average rainfall in Ethiopia if I use CHIRPS or another, or ARC2, average rainfall in Ethiopia, 400 millimeters a year. Average rainfall from ERA5, 800. So it's reporting on average twice as much rainfall as the other ones. And so I think the reanalysis data sets just are great at the global scale, but if you're trying to match those to specific households, you're going to get really wonky numbers. Unless you do some data cleaning ahead of time to eliminate those wild observations, you're going to end up with totally bizarre results. But those are the big outliers. But even among the other subset, CVC, ARC, TAMSAT, and CHIRPS, you will get totally different results for some specific weather metrics, right? So we find mean daily rainfall and total seasonal rainfall to be very consistent across all countries and across all non-reanalysis products. But if you wanted to use z-scores of mean daily rainfall or deviations from long-run average, then we begin to see differences from those, CHIRPS and things like that. And that's because those methods have been updated periodically through time. And so if you go back in time, then you do see deviations in how they're actually analyzing the data.
Thanks. Let me just throw this open and comments or questions from panelists to one another, from the diehard attendees, please. Jules.
I had a question first, and Jeffrey. I think the headline result I understood, but then I was not sure to understand if you offer guidance on which data we should use exactly when we use satellite data. So we shouldn't be too concerned about noise, but then when we have choices between 2, 3, or 4 sources, is there one that is to be preferred?
So that's a second paper. So we have a populated pre-analysis plan that has all the results from the hundreds of thousands of regressions that we ran. The paper is 180 pages long. It's a World Bank working paper, and it's on arXiv. I can send you the link. And so that has all the results, and we have a list of like 7 different recommendations. Here, to get actually all the stuff published, we're now breaking it out into separate pieces. And so this one is on anonymization. The next one is on remote sensing sources. And so I can send you the link. I'll do it in the chat right now to that World Bank working paper. and you can get guidance on that. I will say one thing, as part of the pre-analysis plan, we anonymized the remote sensing sources. So Talip and Siobhan are the ones who generated the data, and then they passed it to us in an anonymized way. So we didn't know what the different remote sensing products were. We just knew it as rainfall 1, 2, 3, 4, 5, and 6, temperature 1, 2, and 3. So all of our analysis, and we've posted it up on archive, all of it was done in an anonymized way. So all we were saying for a while was rainfall 5 is good and rainfall 3 is bad. We've done that to basically try and give credibility to our results, that we weren't predisposed to like chirps or like ECM or whatever.
Okay, thank you.
So Musa, I have a question for you. When you look at just the results, nutrition on current weather shocks, you get no results, but you interpret them as evidence of consumption smoothing. Are you able to show that those are true nulls and therefore evidence of the consumption smoothing, or is it just a lack of power, too much noise in the regressions? Like, just because you get a null, that doesn't mean that it's 0.
Okay. Yeah, so we found in the first stage insignificant result. Then we tried to estimate by changing the definition of our variable. Again, we found insignificant result. Then we go back to the data set and we look the way how they cope. Yeah, the way they cope with the drought shock. They have subjective response. So we found less than 1% of households indicate they changed their consumption pattern to cope with droughts, but the vast majority of them used, like, they sold their agricultural assets or used credits or other mechanisms. So we considered it as
I have a question for Wataru. If I understand right, the analysis you did is to try to unpack how much of the low demand comes from basis risk, where you're trying to quantify basis risk by looking at, essentially by comparing past, by comparing weather losses or weather risk at the household level with the station. And I guess another concern might be that weather is not the only actual source of losses for households. So that's just one dimension of basis risk, in a sense, that the presumption of the insurance product is that weather is the major source of noise and yield. And maybe linking it to Musa's paper, in a sense, the kind of interesting finding, or the striking finding, is how low the correlations are. Maybe it's the finding across much of the literature, how poorly weather predicts crop yields and outcomes. And in that sense, the risks, the basis risk is not of rainfall on the farm to rainfall at the station, it's losses on the farm to rainfall on the station. I wonder if you just comment on that a little bit.
Thank you. Thank you for your great and insightful comment. I totally agree with what you have said. Technically, so in the literature, the basis risk is mainly categorized into like two different basis risks. The first one is the spatial basis risk, which we were focusing on, and another basis risk is product basis risk. So that's the basis. That means that the index is not a good indicator for the crop loss. And then yes, there are a lot of literature that is like showing the product basis risk plays pretty important role. And then yeah, I mean, maybe like that's one of our limitation, because we only focus on the special basis risks. So it could be that if we like reduce the product basis risk, then maybe the farmers would potentially purchase more index insurance. But after hearing the presentation by Jules, I was also like concerned about like thinking about like what is the real the benefit of the index insurance if it is not pretty much beneficial for farmers, or at least farmers do not think so. Then of course the demand should stay pretty low. So yeah, I actually have a question to Jules. So if it does not really have a dramatic impact on the farmers' consumption or like investment, then do you think like it is due to the products of the insurance itself, or maybe it's due to the perception of the farmers on the insurance product? Like, do you have like any thought for this?
Thank you for the question. That's a tough one. I don't know, to be honest, why exactly the effect is low. In a sense, I would say that it also depends what we think is low or high. An effect of 0.10 standard deviation for relatively new products. Okay, it's not transformative, but still it's an effect. And I guess the main takeaway of the paper, we would like it to be that the effect is uncertain, more than what we thought. And the effects are maybe also modest, but they are not so modest. Compared to other intervention, I still believe that estimates that are 0.10 standard deviation higher are worth pursuing. But I also think that the work you are pursuing on improving products design to increase demand is also very important, because the effect we estimate is actually the intention to treatment effect. And so there is a share of households who take up the program. And so for them, actually, the treatment effect should be much higher. So the 0.10 standard deviation is really among the whole population that was offered insurance. This was the increase in investment for them. But within all these people, many people actually didn't take the treatment, didn't take insurance. So I guess the treatment effect on the treated is actually more than 0.10 standard deviation. And one challenge is to increase this share of people that take up insurance. I also had two questions for you, actually, Wataru. I really like the presentation and the paper. So the first one was whether you thought about exploring heterogeneity by the financial literacy or educational level of the people. Because people might understand basis risk differently depending on their background and financial literacy. And so you could see nice patterns maybe there. And also about the outcome variable, if I understood correctly, you look at the number of units that are purchased. And I was wondering if you looked also at the whether household purchased or not at all, like just a dummy instead of having the intensive margin variable.
You mean the binary, right?
Yes, like binary outcome variable.
Okay, thank you. So first, thank you for answering my question. That was really insightful. And answering your second question, actually, like uptake rate for the insurance product was like more than 95%. So most of the household did purchase at least one unit. So that's why we only run that kind of regression. And yes, answering your first question, that's very important point. And yeah, we run several regression, like like simple OS, like regressing these like insurance literacy or maybe like other related things on the insurance demand, but we don't really see any like significant correlation. And then another thing is that so we derive a demand function, right? And then with that demand function, we can actually like predict like how much is the optimal like demand for the specific farmers. But at the same time, we also observe the demand, the actual demand. So what we can do is like we can compare the actual demand and then the theoretically predicted demand, and then we can see differences, and then we regress the other factors on that difference, because that difference means that something unexplained by the basis risk, and then maybe the probability of drought. But we didn't really see any significant correlations. So yeah, that's why I didn't really talk a lot. But yes, I think of course like financial literacy or maybe the trust, because maybe looking at like my demand function, because although in my paper I was like assuming that the farmers only consider the subjective probability, but they make their decision based on their beliefs. So maybe their trust or the financial literacy should also correlate to their objective probability. So yeah, that's the thing that we need to investigate further. But yeah, thank you for your question.
No, thank you so much. Very, very interesting. And actually, we don't find as well heterogeneity with literacy in our study.
Thank you.
Question for both Wataru and Jules. How much, given both of your results, how much do we continue to push the research agenda on index insurance? You know, that JPAL thing, I feel like it was a bit mischaracterized. It's not that demand for index insurance is growing from 2016. It's rather that economists are doing more and more RCTs about index insurance. And now it's, you know, a decade on since I think Clark ran his first one in India. Other than maybe livestock insurance in Kenya, I don't feel like a lot of people want this. Even if we solve the basis risk problem, which has always been like, oh, well, that's the thing that's keeping people from adopting. Like, it sounds like there's not a lot of welfare gains to that. And if the context is so inherently local that no RCT has really any external validity, then we would need to be doing RCTs of specific things all over the world. And is that really a valuable use of our time and global resources? So I'm just wondering, like, what are your thoughts on the future of index insurance or research on index insurance?
I don't know if we have policymakers in the large audience. That would be very useful to hear what they think of the results. But I don't know. I think that there is a lot of work, from what I understand, on how to improve the design of index insurance to make them more impactful. I saw recent papers on that with promising results, and also changing, for instance, the timing of the payments before or after the harvest. And this can have a higher actually effect on demand. So I guess for research, one potential avenue wouldn't be just to test index insurance or not, but different index insurance design within study, such as the study where you had to pay before or after the harvest. But yes, mostly with different products or different design. I think that would be interesting avenues.
I'm conscious that we're about to run out of time, and the system is going to kick us out very promptly. So maybe I can just take the opportunity to thank the presenters. Just a really interesting set of papers, some really thought-provoking results on all sides, right? I think the challenge to it's kind of an old idea in the literature that weather is the main source of variation in nutrition outcomes, as Musa is challenging, that weather is the main source of risk that's affecting farmers, that weather can be measured at levels that are appropriate for the kinds of questions we're asking. So I think there's a wide open agenda here. I think it's a great area for research. And I thought these were really exciting papers that are pushing the frontier ahead. So my thanks to all of you and to the audience who kind of stuck it out to the end. Really appreciate it. And please do stay in touch with each other. I think this is a great community of researchers to continue working on these projects. So thanks to all. And thanks to Suzanne for providing the tech support here. We appreciate it.